SwayamPrabha. Digital India. Educated India.
Hello and welcome to this series of lecture on elements of solar energy conversion. Today here we are at lecture number 19. So far we were analyzing the flat plate solar collector, the temperature distribution and its relationship with the useful heat gain. So, what we obtained so far, that the expression for the useful heat gain, or rather the rate of useful heat gain. Okay. So, few expression we obtained so far. One is this QU is equal to area of the collector multiplied by absorbed radiation minus the loss coefficient, which is multiplied by the average temperature difference between the plate and the ambient. Okay. So, this is the expression, that is the most fundamental or most basic expression we started with while we started looking at the flat plate solar collector. But the problem in this expression is this quantity TPM, which is the mean plate temperature, which is rather unknown, we do not know, right. So, that is why we needed to have alternative expressions. So, this is the first expression we obtained, and the second expression that we obtained was the useful heat gain in terms of the collector efficiency factor. Okay. So, W into F prime, then the temperature difference was not between the plate and the ambient, but between the fluid and the ambient. Okay. So, this is the F prime is the collector efficiency factor, right. So, this we obtain, this we got, this TF is again the problematic quantity we assumed for x directional temperature distribution. We assume that this TF is known at a particular location in the pipe, and that is how we express the useful heat gain by this expression. Okay. So, we have also seen that it is not convenient either. Okay. What is the problem? Because the fluid temperature also is changing along the length, and you do not know exactly what is the value, you do not have a common value, right. So, that is why we needed to have several other expression. We had to do the y direction temperature distribution, we had to look at it. So, which is x and which is y, I am not repeating it here. Please look back at our earlier lectures and you will know the y direction is along the fluid flow direction. Okay. So, this y direction temperature distribution gives us a functional form of TF, which relates the outlet fluid temperature TFO to the inlet fluid temperature TFI. This is the expression that we derived in the last lecture. Okay. But the best thing what we can think of is an expression of the rate of useful heat gain Q u dot, okay, in terms of something that is directly measurable. What is that? The inlet fluid temperature TFI, that is directly measurable. You know what fluid or what temperature the fluid is going into the collector, and the ambient temperature. So, if we can express the QUI in terms of this difference TFI minus TA, then it is the best thing that we can obtain. Okay. So, so far we did not have or we do not have any expression in this kind of relationship. So, what we can propose? So, proposed form of QU, we can write QU dot is some factor which we do not know, multiplied by the collector area and multiplied by the ES minus UL multiplied by TFI minus TA. So, this is what we want, okay. But what factor will come here is not known. That is our goal and that is how we will proceed. Okay. So, let us say this factor, this unknown factor is Fr. Okay, we will see that why that R, what that R stands for, but let us say that for now it is an unknown factor which is Fr. Okay. So, from the expression itself what we can write, this Fr is nothing but Q u dot divided by AC S minus UL TFI minus TA, right. We have done nothing but just rearrange the equation to write it in terms of Fr. Okay. Now, this QU you can write absolutely in terms of the fluid heat gain. So, the temperature difference between the inlet and outlet of the fluid and the mass flow rate specific heat of the fluid. Okay. So, m dot Cp into Tf naught minus Tfi, that is absolutely acceptable form of Qu dot, right. So, what you are writing in terms of the fluid inlet and outlet temperatures only, and the denominator does not change. Okay. So, now what you can do, you can take out few of these non temperature things and write it in terms of temperature only. This is TFI, and here to make it in terms of temperature you have to divide S divided by UL, okay, and the rest of the things is in terms of temperature. Okay. So, just simple algebra we did. Now, what we will do, we will use some addition and subtraction to the numerator, so that we can get a similar form as in the denominator. Okay. So, the goal is make a portion of the numerator divisible by the denominator. Okay. Why we are doing it will be very apparent when we will do it. Okay. So, now what we can write, the expression f r, we can write m dot C p divided by A C u l, this is the prefactor, and now the numerator will change like this, s minus u l minus T f I minus T A. Okay. So, this is the denominator part, we have written it directly. Now, we have to see the numerator part is balanced. Okay. So, we have added s divided by u l, so we have to subtract it, and we have added T A, the ambient temperature, so we also need to subtract it. Okay. So, now you can see, okay, let me write it completely. The denominator is s over u l minus T f I minus T A. So, nothing more we did, we just did some algebra on the numerator, and you can see that in the numerator we had T f naught minus T f I. It is still there, T f naught minus T f I, and all the other things cancel out, s over u l cancels out, and T A, that part also cancels out. Okay. Now, once we have done that, we can see the first term here and the denominator is the same. Okay. So, what we can write, m dot C p A C into u l, and within parenthesis we can write 1 minus s over u l minus T f naught minus T A divided by s over u l minus T f I minus T A. Agreed? Simple algebra we did. Okay. So, now what we will do, we will use the expression that we derived in the last class. So, from y directional temperature distribution, the form we obtained is the following. We obtained that this T f naught minus T A minus s over u l divided by T f I minus T A minus s over u l. This is nothing but exponential of minus u l A C f prime divided by m dot C p. Okay. So, this is from last lecture. Okay. Now, we will going to use this expression. Okay. So, if we use that expression, then this f r becomes m dot C p A C u l minus 1 minus this particular portion is going to be replaced by this exponential function of A C u l f prime divided by m dot C p. Clear? So, from the last lecture expression that we derived, we have used that in the formulation of f r. Now, I bring your attention to this prefactor. Okay, this is the prefactor and this is the exponent. Do you see any similarity between these two terms, the prefactor and the exponent? They are very similar, right? Only difference is it is reciprocal, that means 1 over the other, and we have another f prime inserted there in the exponent. So, the exponent is the point of difference is f prime and reciprocal, that means 1 over x, right. So, what we can do, we can include that f prime thing and derive another factor f double prime to be f r divided by f prime. Okay. Then what we can write, this prefactor will also have the f prime now, because we have divided the whole expression by f prime. So, now we have 1 over exponent of a c u l f prime m dot c p, right. You agree to this? Okay. So, now both the prefactor and the exponent are similar, but only reciprocal. So, what you can write, this thing, this m dot c p over f prime u l a c, this is called dimensionless collector capacity. What do you mean by collector capacity? Collector capacity means if you install a solar flat plate collector, it will give you hot water, right. So, how much hot water and with how much amount of temperature rise, that is your collector capacity, right. So, you can see this expression contains m dot, which is the mass flow rate, specific heat and the heat loss factor, collector efficiency factor and the collector area. So, this is nothing but a dimensionless collector capacity factor. So, I insist that you go and check whether this is actually dimensionless or not. Do not believe me, just go and check for yourself whether it is dimensionless or not. It is important. Okay. So, now we are having multiple factors, right. This f r, even if we did not say what that factor means, it was just a placeholder, right. So, if we look at, yeah, so here it was just a placeholder f r, and then we derived an expression for that, and also at the end we have also introduced another thing which is f double prime. So, it is important, now we have collected few of these factors and also expressed useful heat gain with these factors. Now, it is important that we summarize them all together, otherwise it becomes difficult which factor relates to what. Okay. So, first thing, these new factors, let me just tell them what names we call them by. Okay. F r is called collector heat removal factor. Okay. So, this R, subscript R stands for this removal, okay. And this F double prime is called collector flow factor. Why do we call flow factor? Because it includes the mass flow rate quantity, and that is why it is used to normalize between different size solar collector. So, if you have a big solar collector, if you have a small one, how do you compare their performance? That is where this collector flow factor comes into picture. Okay. These are the names. Now, let me just see how this expression looks like. Okay. So, the final expression that we have here is nothing but this f double prime collector flow factor is your one minus exponential of AC UL f prime divided by m dot Cp, right. So, this is the final expression. Now, if you plot it with this dimensionless collector capacity, f double prime, which is Fr divided by f prime. So, you can see that it will be asymptotically equal to 1 when we have dimensionless capacity to be large enough. Okay. So, it will look like this, and this is in a log log plot. So, if this is 1, this is 10, this is 100. So, it is a semi log plot, and this is an exponent expression. So, it is useful to plot it in a semi log plot. Okay. So, here I should write that this collector flow factor, what it does, it helps to express the performance of the collector in terms of non-dimensional capacity. So, when you have a non-dimensional capacity, you can compare across different sizes of the collector. So, which helps in comparing across different sizes of a collector, right. Okay, fine. So, let us look at, okay. So, now we have to somehow summarize what we did by all these thermal analysis that we did for the flat plate collector. So, the most useful expression that we obtained so far is the ACFR minus multiplied by S minus UL TFI minus TA. Okay. This is the most useful expression of the rate of useful heat gain in terms of the inlet fluid temperature and the ambient temperature. Okay. That is what the collector heat removal factor does. Okay. So, here I want to bring your attention to the heat exchanger theory that you have learnt in your heat transfer courses. Okay. So, there you have you have seen that there was one quantity called heat transfer effectiveness. Okay. So, that effectiveness relates you to the actual heat transfer, okay, to the maximum possible heat transfer, right. That is the effectiveness quantity we you have seen. So, here also this is at the start only I have told you that solar flat plate collector is nothing but a heat exchanger, but a little bit complicated heat exchanger you can say, where most of the parameters are unknown, and that is why all this complicated formulation is required to analyze it properly. So, if we bring down that heat transfer analogy again, what we can write, that the maximum possible gain in useful heat is possible when the loss is minimum, right. That is the basic underlying philosophy, that if you want to maximize the gain, you have to minimize the loss. Now, in the above expression here you can see that the temperature difference comes with the loss factor, okay, UL is the loss factor, and that particular part is minimized when you have TFI minus TA to be the minimum, right. So, loss is minimum when TFI minus TA is minimum, is not it? Okay. So, that is the minimum loss point, that what we will compare with the actual heat gain to get the effectiveness. So, now let us summarize. We have seen all the concepts. Now, we will summarize how to use them. So, here what is happening physically, when your mass flow rate increases. So, this delta T outlet and inlet. So, temperature difference between the outlet and inlet, this drops, right, and FR increases, okay. But this increase is limited by F prime, right. So, this is collector efficiency factor. So, even for very high mass flow rate, collector temperature will always be greater than the local fluid temperature, right, and that is why Fr, this collector heat removal factor, is always less than equal to F prime, okay, and that is what sets the limit for F double prime, which is always less than equal to 1, right. That is what we have seen in the earlier plot. So, just to summarize these different F, first one we have seen is simple F, which we called Finn efficiency, okay. And what does it relate to? It relates the heat transfer from the plate to the fluid carrying tubes. Okay. So, that is the first step we have looked at, it is Finn efficiency. Now, next one was the collector efficiency factor, which is designated as F prime. Now, what it does? It relates useful heat gain compared to the case when the absorber is at local fluid temperature. Okay. So, this relates the useful heat gain in terms of Tf minus Ta. Okay. This one, the first one was Tpm minus T, or rather Tp minus Ta, that is the relation. Now, the collector efficiency factor F prime brings it to Tf minus Ta, and the collector heat removal factor, this is the new one, collector heat removal factor. So, it brings this Qu and it relates Qu and this Tfi minus Ta. So, we are not interested in the fluid temperature anywhere, but the inlet. Okay, that is how the Fr came into picture. So, what I was trying to tell you earlier, that it is equivalent to the effectiveness of a conventional heat exchanger. Okay. In terms of it relates the actual heat exchange to the maximum possible heat exchange. Okay. That is the definition of heat exchanger effectiveness, and collector heat removal factor Fr does exactly the same thing. And the last one is F double prime, which is Fr divided by F prime, and it is a non-dimensional form of the same equation, which the useful heat gain in terms of the collector heat removal factor F double prime makes it a non-dimensional equation, and that is how it helps comparing several differently sized collectors. Okay. Now, before I move on, I want to say something about the critical radiation level. So, we have seen that the useful heat gain rate can be written in terms of the collector heat removal factor, which is S minus UL Tfi minus Ta, right. This is the most useful form of useful heat gain. Okay. Now, what is this S? S is the rate of absorbed heat from the solar radiation, right. So, we can write it in terms of this effective tau alpha into the intensity on the tilted plane. Okay. So, this is nothing but S, and here this thing is the effective transmissivity absorptivity product, and here we are not distinguishing between the beam part and the diffuse part. We are taking an effective value according to the average absorption, okay, and averaged over beam and diffuse radiation, okay. And the other part is the intensity on the tilted plane, right. So, this is S. Now, you may have a situation where you are actually have very low intensity and still you are running the flat plate collector. So, what would be the consequence? Let's see that. Okay. Now, let me write it that the critical radiation level is defined as the limit when useful heat gain is 0. So, here in this expression you can see that this first part is the gain and the second part tells you about the loss, right. Now, when this gain and loss will be equal, QU will be 0, right. So, when QU equal to 0, then what we can write? We can write that this ACFR, or rather S will be equal to UL TFI minus TA, right. Gain will be equal to loss, and if you write this part, and this is for critical, C for critical will be equal to TFI minus TA, okay. So, this stands for critical radiation level. So, which you further can write in terms of ITC will be equal to UL TFI minus TA divided by tau alpha effective, right. So, you can see that if the solar intensity on the collector is having this ITC value, you are not gaining anything, you are just gaining 0, okay, because whatever you are gaining is being lost to the atmosphere. So, that is how we find the critical intensity level below which you just cannot run the collector. If you run it, you are expending energy in running it, okay. You have to run the pump. So, you are expending energy, but you are not gaining anything. So, what you should do? You should only run the collector when your intensity is above this critical value, is not it. So, what we can write, this QU ITC and positive, we put this sign positive here, okay. What it tells? That only when this IT minus ITC is greater than 0, you you run the collector to have some QU, otherwise do not run the collector, it will be loss for you. You understand this? So, that is why this particular, for most of the or for any solar collector, if you buy from the market, it will tell you what would be the ITC for that particular collector. That will tell you that below that level you do not run it, you just let it stand there, do not run fluid through it. Okay. Now, what we will look at few variations of the flat plate collector. So, few geometrical variations of flat plate collector. So, we have completed for the basic geometry, we have completed the analysis. So, we can use those analysis directly, and what we can write. So, what is the first one is the basic geometry. Let me just summarize last few lectures. Okay. So, this is the plate where you have these tubes. Okay. Plate has certain thickness, let us say this thickness is delta, okay, and the pitch of this tube is W, and for each tube we have some D. So, earlier we distinguished between the D outer and D inner, but for thin tube, for thin tubes what we can do? We can use a common D, which is dI plus D naught by 2. Okay. So, that value is our D, and what we have seen that this bottom portion is completely insulated, and we have still we have certain loss from the bottom, and we have a cover system here placed on it. This is the cover, and through it we have a effective loss coefficient UT, top loss coefficient. Now, for this basic geometry, the thermal resistance circuit tells us that our UL will be equal to UT plus UB, because they are connected parallelly. Okay. So, if that is the case, we have derived the expression for this collector efficiency factor F naught to be 1 over WUL pi dH. This H, small h, stands for the heat transfer coefficient inside the tube, and WUL divided by the conductivity of the bond material between the plate and the tube, plus W by D plus W minus D F. This F is the fin efficiency. Okay. So, for collector efficiency you need to first get the fin efficiency factor. Okay. And where this fin efficiency factor, you have obtained the expression okay, and this is called fin efficiency factor, and this is called collector efficiency factor. Okay. So, we have written nothing new. This is the expression we derived for last couple I mean few lectures, 2-3 lectures. Okay. And here this m square is UL divided by k into delta. And once you have this f and f prime, the transition from here to find f r or f double prime is same for any geometry. So, I am not writing that, I am only going to look at if the geometry is changed, how your expression for f and f prime changes. From there f r and f double prime are obtained exactly the same manner. Okay. Now, let us look at the next variation in geometry, when the tubes are placed on the top of the plate, top of the absorber plate. That is also a possibility. Okay. So, here again we have the same thing, everything same, only this is completely insulated. Okay. And the tubes are on the top of the plate, not at the bottom of the plate, but on the top, and then you have this cover. Okay. And you have this ut and ub. Again this ul is nothing but ut plus ub, because you have parallel connection, right. And the expression that gets affected is f prime, that the collector efficiency factor. Okay. And we are not going to derive it, but we are going to simply write it. Okay. Okay. So, now you see in the when the tubes are at the bottom of the plate, you have this particular expression of f prime, right. But now you have a separate expression of f prime, because the heat transfer, the resistance circuit itself changes. Okay. Now you are exposing the tubes directly to the loss of the ambient through radiation, and it also exchanges heat with the cover, right, through radiation as well as convection. And here this fin efficiency factor stays the same. So, how from the plate to the tube heat moves, that part stays the same, but from there how it is exchanging heat with the fluid and releasing that heat to the or losing the heat to the ambient, that part changes due to geometry. Okay. Then the third geometrical variation that we can have is tubes are halfway exposed to the top and halfway exposed to the bottom. So, if we have some plate, tubes are embedded in it. Okay. So, it is halfway exposed to the top and halfway exposed to the bottom. So, tubes here are halfway exposed to the top and halfway to the bottom, and we are also assuming. So, that is the first geometrical variation, and we are also assuming that the plate thickness is negligible to the tube diameter. Okay. So, what we can do, we can redraw this with negligible tube thickness, and we have these tubes and plate thickness is negligible, and rest of the things are the same. Here you have cover, here at the bottom you have insulation. Okay. Again you have some top loss coefficient, some bottom loss coefficient, and this total loss coefficient will be UT plus UB because they are parallelly connected. And again you see the difference that you obtain in case of the collector efficiency factor F prime. Pi dH plus W d plus W minus d into F, and F is same as in case of 1 and 2. So, 1 and 2 means the prior two geometries that we have talked about, F will be same, the fin efficiency will be same, and F prime is the one that is getting affected by the geometry. And once you have F prime, the relation from there Fr the heat removal factor and F double prime which is collector flow factor, all of these will be obtained by similar method. Okay. So, now let me show you a real picture of a flat plate collector which I have not shown you earlier. So, okay, here we have a actual flat plate collector, okay, and I should put the image cursor that is obtained from the book by Sukhatme and Nayak. Okay. So, this photograph is taken from that book, and all the details of the book is mentioned in the first lecture where all these details were mentioned. Okay. So, here you see that we have a tank and we have a tilted collector. What would be the angle of tilt? That will depend on where you are placing it. Optimally, it should be the latitude of that place, and you have to orient the angle, orient the collector towards the equator. Okay. If you are in the northern hemisphere, it should be facing towards south, and if you are at the southern hemisphere, it should facing towards north. Okay. So, yeah. So, here you can see that these ridges, they are nothing but the tubes, okay, and the whole thing is black painted and it is under operation. That is why glare is being seen here, and that is how a flat plate collector works. Okay. And another thing that you can have this array of flat plate collector. When the temperature requirement is large, just one flat plate collector does not give you the required temperature rise. So, what you do? You put arrays of this collector, and all of them are connected through inlet and outlet manifolds, and then you have a tank outside of this array of collectors. Again, the image cursor is from Sukhatme and Nayak book. Okay. So, this is for larger capacity requirement or bigger temperature rise. Then in case of this requirement you have arrays of these collectors. Okay. So, let us stop it here. Then in the next class we are going to tell you about few more variation used in the field. For the basic flat plate collector we have derived, described and we have analyzed it thoroughly. So, in the next class we will see few more practical variations that are employed and we will also see how do we test and find the specification for a given design of flat plate collector. Thank you for your attention.